Hi everyone. I hope you are having a fantastic week. So let's start with our today's topic. So today we are going to discuss about force fields and what molecular simulation is all about, what's the basis of molecular simulations. But before jumping onto that topic, I would like to take you through a story of why molecular simulations is something that we should all look forward to and what are the limitations of molecular simulations and but before that, what are the limitations we already face with traditional methods like optical microscopes, right? So the thing with, firstly, let's just skip human eye. We all know that human eye is mostly irrelevant when we are looking into finite, smaller biological molecules, right? We just can't see anything. So let's start with optical microscopes. The range of optical microscopes is around 200 nanometers or so. Why is that? That we cannot see objects smaller than 200 nanometers in our optical microscope? There is a German physicist back in the old days. They have found a law which basically, connects you with this problem, which is what is the smallest object that you can resolve using optics. So I'm not saying optical microscope, I'm saying optics. Because optics here means with light, with a visible light to be more specific. So the thing is, they have found this correlation where they've given this equation, which is here D is the smallest resolvable object length. Here lambda is the wavelength of the light that is being used here, and then we have 2 into numerical aperture. So here the numerical aperture is basically n sine theta. Here theta is, I think, half the angle of I think some kind of light entering the lens or something like that. You can check that out. It's called Abbe's principle. It's This equation has been given by Ernst Abbe. But what we are trying to find here is, if let's say we have a microscope that is a dry microscope, that the most possible maximum value of Na that is possible there is 0.95. 1 is the ideal condition. If Na is equal to 1, it's like the ideal state. So let's say we are using a visible length of visible what do you call visible light having a wavelength of 400 nanometers, and if we use an ideal lens, then it's basically 400 divided by 2 into 1, right? And we will get something about 400 divided by 2, which is 200 nanometers. So that's what I have quoted here, that why can't we see things smaller than 200. But then there are some experiments have been done where people don't use dry lenses, but then they put a drop of oil on top of the lens, and then they put a cover slip. By doing that, they can increase the maximum numerical aperture of the lens. Like, it can attract now more light, just because there is a layer of oil in there. It can now attract more light, or another way, you can say more information, whatever you want to say that. But the interesting part is, by doing that oil layer, they can actually increase the numerical aperture of the lens. And now if we calculate that, that comes to about 143 nanometers. So just a small jugaad, how we call in India, you can actually increase the efficiency of lenses. But that's one thing. Now coming back to our original question, which was, what do we do if we have a problem or a problem object that is smaller than that 143 nanometers? What do we actually do? And back in like 100 years ago, there was not much answer. And people back in those days, people started coding, right? These personal computers started came coming in, and people started coding. So I don't know who started it, but somebody might have already guessed that let's just recreate this, cells atoms in a computer, and that have gotten really better nowadays. So there's a full fledged of simulations that you can actually do, starting with finite element methods. It's like used for continuum theory and stuff like that, and all the way to ab initio DFT methods. So, but our interest is somewhere here, right? This course will be focused on classical MD and course training. So this is our area of interest. That comes to about somewhere around nanoscale, right? So let's say our system size is about 10 nanometers. So that's clearly 10 times smaller than the like the optical limit or the diffraction limit. So we can't see those things inside the cell. That's the problem. So let's start with our problem, which was force field or the basics of force fields. So what our basic computer simulations are like. If I have to ask you, what do you think about computer simulations? And the answer, the kind of answer usually naively people put in is that you can actually study, like you can actually, without doing an experiment, you can know what is going to happen. That's the usual answer that people get or people say, right? But I would rather put that into a different perspective, and that's my job here, is to create a new perspective in your mind, which is computer simulation is a way where if you put garbage in, you will get garbage out. That's my favorite line. Why I say that? Because computer simulation is nothing other than just a lot of guesses that has been made in the past, and those guesses are almost right. I'm not saying it's fully right, but I'm saying almost right. So what are these guesses? So think that you have a, let me just start the laser pointer. So think that you have about a couple of water molecules interacting with each other, or let's say for the sake of simplicity, think of this as an gas, argon gas or something like that, and they are interacting with each other. Very light, like this is not a very strong interaction, so it's a very light interaction. So let's say these argon molecules are just interacting with each other with Lennard-Jones potential or something like that, right? And what happens when you do that in a large scale of atoms? Let's say you have 1 million atoms or something like that, and you do that for a very long period of time using statistical mechanics. You get pretty good prediction of the bulk properties. So what are the bulk properties? Let's say the density, the viscosity, the diffusion coefficient. If you are working with protein, the radius of gyration. Now, so what is the actual guess that I was talking about here? If you think properly, like how do we find in a real system that one argon molecule exerts what amount of force on the other argon molecule? So there are theories around it, but are those theories 100% valid in the real world? I doubt. So those theories are an approximation, like theories are always an approximation, right? Somebody approximated something in their theory, right? And if you let's say in computer simulations, if you use hundreds of those theories, you have done probably, and every single theory might have five approximations. So you're coming down to about, I don't know, 500 approximations to get to an equation um, which explains how these argon molecules interact with each other. So I just said equation. The other way, or the more formal way, would be a simulation, right? Because simulations is just a bunch of equations in real time calculating how one molecule interacts with each other. So basically, that's simulation. So coming back to the original question, so we provide a guess between what is the strength of attraction or repulsion between these two argon molecules. and in return I get some bulk properties of that whole system. So that's exactly what we are getting. I have planned a small experiment for you. Maybe in the later videos I'll provide this with a more with more information how to do that. So basically, this experiment will be our first experiment, which is we will start with a simulation of, let's say, 10,000 or 20,000 argon molecules, and we will add 10% Lennard-Jones potential. We will like increase the Lennard-Jones potential by 10%, and on the other system we will decrease the Lennard-Jones potential by 10%, and we will see how these bulk properties changes. Like you can add any other properties as well. So that is now done. So now we have got an idea about what are these guesses at the interactions, right? And we do it everywhere, to be honest. Lennard-Jones potential is already an approximation of how non-bonded particles interact in a non-Coulombic situation. So Lennard-Jones potential is not the right term to really start with, but that's again, it's just an approximation that we have used in computer simulations. And there are better ways to describe two particles that are interacting with each other in a non-charge environment, right? So we'll come to that. We will like in the later part of the video, we will, not on this video, but on later part of the course, we will go through all of these different, forms of, let's say, force field. I think it's is the right time that we should start calling them force fields. So what is a force field? Force field is basically thousands of thousands of guesses that has been made, guesses plus some research work, where they like try to calculate how much interaction between two different kind of molecules is there. Let's say this was a very active field of research like 20-30 years down the like in the past. So in those days what used to happen was that you keep on improving the force field. So how do you improve the force field? You take one pair of problem, which is like, let's say, an phosphate molecule interacting with an oxygen, and they just try to find out what or how do we change these interactions in a way that we get a better bulk property, right? And they do it over and over again for thousands of times by different set of researchers, and we have now got some of the good force fields like charm 36, amber force fields. GAF is there for organic molecules. So these force fields, like the work has been done by last, I don't know, 30-40 years, and now we don't realize that back in those days they used to make guesses, try out things, see if it doesn't work, they like change the some small tweaking is done, and they try to improve the force field. There's one example or two examples just in front of you, which is charm 36M is just a small refinement over charm 36. So what was the problem? Charm 36 has a very stiff backbone. So if you, let's say, do intrinsically disordered protein simulations, then you will get like those IDPs won't, they won't be like flexible as it should be in the nature. So I have so just one suggestion here. Maybe you do this mistake or maybe you don't. I have seen many people doing this mistake that they just choose one force field and then they look into the result and then they just say, well, simulation says, this molecule is not good enough for that protein for binding for whatever reason is there, like whatever you are trying to research, but they just try one force field and then they just say it's not good enough, we need to find a new molecule. Well, sometime you might also want to consider that you might want to change your force field and see if your molecule works better, or the Contrast will also work, right? Let's say you have used this amber force field, and whatever thing you were like researching, it just melted pretty well with that whole cohesive idea, and you are just saying that force field is right. But what about there could have been a better force field that would have suggested that your protein or your molecule doesn't work? And these are very tricky questions to answer, to be honest. Like, I don't have an answer for that, and probably you won't have an answer for that as well. But I think somewhere like sixth or seventh week, we have planned one week where we will teach you how can you improve your own force fields. So I think that will be very interesting for you guys, that you can change force field in real time based on what are the experimental data you have and stuff like that. But we will come to that later. Now you have got an idea that there is something, a set of collection of parameters that is called force field. This is basically you have to understand. If you don't understand that well yet enough, then let's go to our new slide, which is um, as you can see here, like this Lennard-Jones potential is there, Coulomb potential is there, harmonic potential is there, improper dihedral potentials are there, and as I was saying back then that these Lennard-Jones potentials are not good enough. So a slightly more improved version would be a Morse potential, but we will come to these details in the later videos. This is just an idea for you to understand what a force field is. So what is a force field? Let's say we are working with Lennard-Jones potential, and you see there's something that we are writing here, which is Rij, which is basically two molecules, two different molecules, right? I is one molecule. Let's say this is a water molecule, right? And let's say there's a J, which is hydrogen of some other molecule, right? Let's just think about this like this. This is an oxygen, this is an hydrogen, and they are not bonded. So they are in a non-bonded setting. So in that condition, what will be the epsilon ij and what will be the sigma ij? How do you know that? So we actually, me personally, when I'm doing the simulation, I don't know what is the epsilon value and what is the sigma value of that particular set of interactions. But the interesting fact is these numbers will be different in all the different force fields, right? So what is exactly a force field? I'm sorry, I just got distracted with that main idea, which is a force field is just a collection of eij's, sigma ij's here. There is this epsilon naught is there, epsilon r is there. There is this k term is there. There's a lot of k terms. There's a lot of n here. Epsilon some, I don't know, shy or something it is called. So all of these terms are basically hyperparameters. Why do I don't need to really understand what is this called? Because whatever you see that is a hyperparameter, that's probably in your force field, somewhere in your force field. You just need to know how to find it. So we will actually go through that as well. But before that, I would like to emphasize that how does a force field works. So let's say you have 10,000 entries of different kind of interactions. For example, oxygen, hydrogen, oxygen, nitrogen, nitrogen, potassium, potassium, argon, whatever, right? All these different kind of permutation combination that you can think of, and also like carbon in a double bond, carbon in a triple bond. These are like different variations of carbon, and all of them will have different hyperparameters for different situations, right? And all of this is actually recorded in your force fields. That's the interesting part. So how to actually find it? We will actually do this experiment in the first experiment that I've just showed like one or two slides ago. So you will actually try to find from this force field what are the epsilon and what are the sigmas you're looking for, and you will try to do this 10% up and 10% down experiment, which is I think pretty good. to start with. So, coming to our small demo, right? So, in the force field, you will have sigma AA. Let's call two molecules. So, here's a set of five molecules. All of them are named with A, B, C, D and with different colors. Now, in the repository or in the force field, you will find the sigma value of A and the epsilon value of A. And you have to find, since as you can see here, you have to find the sigma value of AB, to be honest, right? Of two different kind of molecules interacting. So if you are looking for this interaction strength, then you need to know what is the sigma of AB, but that's not in the force field. So how do you calculate that? You use Lorentz Berthelot's rules. And what it says that one is a geometric mean and the other one is just sum and divided by 2. I think it's called arithmetic mean. So if I want to find the interaction between A and B, what I'll do, I'll use sigma AA and sigma BB. I'll just add them and I'll divide it by 2 and I will have the value of sigma AB. Same I'll do with epsilon. So now I have actually have the value of epsilon, I have the value of sigma AB and here also sigma AB. The only difference that is left is the R, right? Now the question is that once you have that value of, let's say you have this value of, this is you have, this you have, and this you have. If you remove those things, then it's basically just a non-linear function of R. And what is R here? Distance between A and B. So you will actually get the classic example of Lennard-Jones potential, which looks something like this, and you might have already seen some potentials like that. So if you actually do this experiment with let's say one like two interacting molecules, and you take that epsilon and sigma value from the force field, let's say you choose a charm 27 or something, you go inside and you find these parameters, you put that into an equation, and you change the distance between A and B, like you can actually retrieve this curve, and probably this is also something that we are going to do as an experiment because it's fun and it's also gives you a very clear perspective of how to use a force field. Okay, so for now this part is done. We have completed the preliminary like the basics of force fields, and the next step we'll dig deeper into some of these key topics.